Sequence impedance and sequence network of synchronous machine. Sequence impedance definition. The sequence impedance are the impedances offered by the devices or components or circuits for the sequence component of current. The sequence impedance of the network describes the behavior of the system under asymmetrical fault conditions. There are three sequence impedances: positive sequence impedance, negative sequence impedance, and zero sequence impedance. So positive sequence impedance, the impedance offered to the flow of positive sequence currents is known as positive sequence impedance. It is denoted by Z plus. And negative sequence impedance, the impedance offered to the flow of negative sequence current is known as negative sequence impedance. It is denoted as Z minus. And zero sequence impedance, the impedance offered to the flow of zero sequence current is known as zero sequence impedance. It is denoted as Z naught. Consider a three-phase synchronous machine with neutral grounded through an impedance Zn. So this is your synchronous machine representation. The A phase having a generated EMF EA and the synchronous impedance Zs. Similarly for B phase and C phase, and the current at A phase is IA, B phase IB, and C phase IC. Then the corresponding phase voltages VA, VB, and VC. And the neutral is connected to ground through an impedance Zn. Let this VA, VB, VC are the phase voltages, and IA, IB, IC are the phase current. Now using KVL, the line to neutral voltages can be written as this VA value. This will be equal to the generated EMF minus the drop across the synchronous impedance and the drop across the neutral impedance Zn. So the drop across synchronous impedance is Zs into IA minus Zn into IN, the drop across the neutral impedance. Similarly for B phase, VB equal to the generated EMF minus the drop across the synchronous reactance, the drop across the synchronous impedance minus the drop across the neutral impedance. VC, generated EMF minus the drop across synchronous impedance minus the drop across neutral impedance. In the similar way, we can form this equation. Substituting the condition for the unsymmetrical fault analysis, the sum of phase current IA plus IB plus IC is equal to the neutral current IN. So while substituting this value over here, instead of IN, I am going to substitute IA plus IB plus IC. So the equation become VA equal to EA minus Zs into IA minus Zn into IA minus Zn into IB minus Zn into IC. Similarly for other two phases VB and VC. So now VA equal to EA minus, taking IA as common, we will be getting Zs plus Zn and minus IB into Zn minus IC into Zn. Similarly for B phase, taking IB as common, so we will be getting Zs plus Zn, and similarly for VC, IC as common, I am getting the two term Zs plus Zn. So this is your third equation. And representing this equation, third equation in matrix form, so VA, VB, VC, and here is the generated EMF EA, EB, and EC minus the complete Z matrix, that is Zs plus Zn, here Zn and here Zn. So taken minus as common here, all the coefficients of IA, IB, and IC forms the Z matrix into IA, IB, and IC. So this is your fourth equation. It is a matrix form of the voltage equation. And in simplified form, we can represent the voltage, phase value of voltage as Vp, and that is equal to the generated EMF matrix as EP minus the Z matrix as ZABC into the phase current IP. So this VABC equal to EABC minus ZABC into IABC. So phase can be represented as ABC phases. So instead of substituting P in the prefix, we can write ABC. So VABC equal to the transformation matrix T into V012. This 012 represents zero sequence, positive sequence, and negative sequence. 0 represents zero sequence, 1 represents positive sequence, 2 represent negative sequence. So this V012 is a symmetrical component of voltage, and that will be equal to, in generated EMF also, instead of EABC, you can substitute the transformation matrix into E012 minus ZABC capacitors, and IABC can be converted into transformation matrix into I012. So considering the seventh equation, and now multiplying this seventh equation with the T inverse on both sides. So multiplying T inverse on both sides, you will be getting this expression, and T inverse and T get cancelled. So you will be getting V012 equal to E012 minus this whole term, that is T inverse ZABC into T, that will be equal to Z012 into this I012. So Z012 equal to T inverse, the transformation matrix inverse, into ZABC into T. So we are going to find this Z012. Z012 equal to the T inverse matrix is 1 by 3 and this complete matrix 1 1 1 1 A square 1 A square A, and this ZABC previously we determined, so that we can substitute here, and the T matrix is 1 1 1 1 A square A 1 A square, the transformation matrix. So by doing the matrix multiplication of this three term, so we can obtain this Zs plus 3Zn and the remaining two terms are 0. So similarly for the second row 0 and the Zs and 0 and 0 0 Zs. So this is your Z012 matrix, and this first term is your zero sequence impedance. So it can be represented as Z0, and this is Z plus positive sequence, and this is negative sequence Z minus. This is your equation number 9. Since the generated EMF is balanced, there is only a positive sequence voltage EA. The negative sequence and zero sequences are 0. So E012 equal to 0, EA and 0. Only the positive sequence voltage alone present. So the equation 8 becomes, so the equation 8, this 8th equation can be written as this VA0, VA plus VA minus equal to 0, EA 0, only positive sequence voltage alone present, minus the Z012 matrix into IA0, IA plus and IA minus. So now you can expand this matrix. So VA0 equal to 0 minus Z0 into IA0. So that is equal to minus Z0 into IA0. This is your VA0 value. Similarly for VA plus, it is EA minus Z plus into IA plus. And VA minus is 0 minus Z minus into IA minus. So like that we can expand this matrix. You can get the symmetrical component of voltage. Now sequence network. Definition: the single phase equivalent circuit of power system formed using the impedances of any one sequence only is called the sequence network. There are three sequence networks. One is positive sequence network, negative sequence network and zero sequence network. So positive sequence network for a given power system shows all the paths for the flow of positive sequence current in the system. Negative sequence network for a given power system shows all the paths for the flow of negative sequence current in the system. And zero sequence network for a given power system shows all the paths for the flow of zero sequence currents. Now we are going to draw the sequence network of a three-phase synchronous machine. So there are three conditions. The first condition is a three-phase balanced generator grounded through an impedance Zn. So for that, the zero sequence network will be considering the zero sequence impedance. It has two terms. One is synchronous impedance and 3 times the neutral impedance. So this we obtain from the Z matrix from the derivation, and Zs plus 3Zn, that is your Z0, and the current flowing is IA0, the zero sequence current, and voltage is VA0. So this is your zero sequence network. Similarly for positive sequence network, the generated EMF will be present only in positive sequence network, and followed by will be having a positive sequence impedance, and the current is a positive sequence current IA plus, and VA plus is positive sequence voltage. And in negative sequence there is no generated EMF, only the negative sequence impedance, current and voltage. And the second case, solidly grounded three-phase generator. So the generator is solidly grounded, there is no neutral impedance connected to the neutral terminal. So the terminal is solidly grounded. In the zero sequence you have to just short those terminal, so it is solidly grounded. And the positive sequence and negative sequence network remains same as the previous case. And third case, ungrounded three-phase generator. So neutral is not grounded. So in such case, you have to represent the zero sequence network as the open circuit condition at this point, and here you'll be having a synchronous impedance, that is zero sequence impedance here, and the current and voltage. Then similarly, for positive and negative sequence, the circuit remains same as the previous cases. So this is your sequence impedance and sequence network of synchronous machine.